All right, gang, Math 6620 here. What we're going to do in this video, and I suspect that this is going to be a rather lengthy video, and I have no idea how long it's going to take, obviously, is I want to look at a complete example of a principal component analysis and factor analysis. In the previous video, what I did is I gave you some matrix techniques, and we're going to revisit those. But I wanted to go ahead and get on the books a complete example using R. It turns out that if we have a raw data, then we're going to run principal component analysis, factor analysis. It's best to use R. But sometimes we're just not given our data set, but we're just given the summary of our data with a correlation matrix. What you're going to need to do in this situation, and you'll probably have a homework assignment that'll require you to do this, is you'll use matrix operations. Now you can use R, you can use Mathematica or whatever may work for you, but you clearly would need to use matrix operations if you're just given the correlation matrix. All right, gang, a lot of stuff going on here, and I'm sitting here trying to kind of get my mind wrapped around all this. Let's go ahead and talk a little bit about the data set that we're going to use here. The data set I have here is some placement information that I got my hands on, and what this was, or at least my understanding of this is something that was collected from I don't know, 73 high school students, and what they did is they gave a kind of a placement test, or at least an achievement test, if you will, of 6 subject areas in mathematics: calculus, trig, problem solving, logic, statistics, and algebra. And what they did is they gave 50 questions in each. So they gave 50 questions in calculus, 50 in trig, and so on and so forth. This first student that I've got highlighted here got 9 questions out of 50 correct in calculus. They got 12 questions out of 50 correct in trig, 3 questions correct out of 50 in problem solving. Sounds like they need to work on their problem solving skills. And, you know, at the end, 21 questions out of 50 in algebra. Now, the purpose of principal component analysis and factor analysis here is kind of twofold. First of all, I'd like to examine this, so I'm going to go back to this. So our purpose is twofold. And I think I called this math skills .csv, and I think that's the way it's presented on Blackboard. So our goal is twofold. I want to use PCA and factor analysis to see if I can identify an underlying structure, you know, that's not just visible with the human eye. The second thing I'd like to do is I suspect that some of the variables are highly correlated. So if I wanted to use this data in multiple regression techniques, then I have a multicollinearity issue. Guys, remember when your predictors are highly correlated, let's say, for example, that we wanted to use calculus and trig and all these different scores to predict, for example, how someone would do on an ACT or whatever it may be, I would have a hard time using all these variables because they are probably so highly correlated, and I would get into a multicollinearity issue. So what I want to do is I want to examine to see if there are any components that pretty much does an adequate job of explaining the variation that these 6 variables explain. Okay, so I want to see if there's any underlying structure that can help me achieve 2 goals here. And I think this actually turns out to be kind of cool. Now, first thing we need to do is some preliminaries. And preliminaries that I have, do we have any low correlations? High correlations? Sample size issues? And do I have a normality issue? These are preliminaries that I'd want to take a look at before I begin a principal component analysis, okay? Now, the first one is low correlations. Typically, when I have a lot of correlations below 0.30, then that could be problematic, okay? Now, again, what is a lot? Well, a lot is clearly subjective, and I presented it that way on purpose. So, guys, what it looks like to me, I'm getting ready to crunch some data, so I need to bring R into play. Again, I'm pretty sure that I called this math skills. Cool. All right. So the variables, I like to have those easily accessible because, you know, obviously if the C is capitalized, it makes a difference. Now, first thing I want to do is take the correlation. So look, create the correlation matrix. And I don't know, people are different, obviously. That bothers me that all these correlations are presented to 7 places. I prefer 2 or 3. So I'm going to round the correlation matrix to 3 places and just clean it up a little bit. So guys, I got tunnel vision right now. Do I have too many small correlations? Well, when I look down calculus, I see that I've got 1 that's below 0.3. Just focusing on the ones below 0.3 right now. I've got 2 in trig below 0.3. I've got 1 under logic, 2, 3 under stats. So I've got issue to investigate this low correlation issue. So guys, here's the way we do that more objectively and more technically. What we run is we run a Bartletts test of correlation matrix. Now, guys, let's, well, let me back up a little bit. What the Bartletts test of correlation matrix does is it compares 2 matrices. It compares the identity matrix with our correlation matrix. Okay? Now, let's think about the identity matrix. Let's say, for example, that we are looking at the correlations between variable 1, variable 2, and variable 3. Now, obviously, in this situation, we have 6 variables, but let's just say, hypothetically, we're looking at 3 variables, okay? We know on the diagonals we're going to have 1 because every variable correlates perfectly with itself. But let's assume that V1 and V2 aren't correlated, V1 and V3 aren't correlated, and V2 and V3 aren't correlated. Well, if you think about it, if we have no correlation between V2 and V3, V1, V2, V3, we would have exactly the identity matrix. Well, what we can do is we can compare our matrix to this to see if the difference is statistically significant. Because we want our correlation matrix to differ statistically to the identity matrix. And it's really kind of cool because that's exactly what Bartlett's test does for us. Okay? So Bartlett's test, the null hypothesis. Is our correlation matrix is equal to the identity matrix. And the alternative is our correlation matrix is not equal to the identity matrix. Okay? Now, guys, clearly, P's greater than 0.05 are problematic, because what would happen with a p-value greater than 0.05, we would fail to reject the null, which would lead us to believe that there's not enough difference between the identity matrix and our correlation matrix to assume that we don't have too many low correlations. So we kind of hope for statistical significance here when we run this. Okay? Now, let's... Now, the command in R is called core test Bartlett, and we just run this on our data, okay? But to get this option to pop up in R, we have to install what's called psych package. All right, so let's get out of here, go over to R, and let's see if we have too many low correlations. So I need to install packages. Select a crayon. Someday. Okay, this is annoying. Don't you just hate the spinning wheel? I was doing some stuff this morning and I probably should have restarted my computer. Anyway, you finally get that. Choose our buddies from UCLA. Actually, I'd call them my buddies. I've never met those guys. Wow, this is taking forever. All right. So library, psych, and we're set to go. So guys, we're going to run the core test, Bartlett, of our data. You'll see that the underlying probability distribution is a chi-square distribution. We have a chi-square statistic of 180.3, extremely high. We have a p-value that's negative 30, so very, very, very low. And degrees of freedom equal to 15. All right, so what we conclude that here is our p-value is less than 0.01, so low correlations are not an issue. All right, gang, what about high correlations? High correlations are much easier to address. Again, Bartlett's correlation, or Bartlett's test examines low correlations only. For high correlations, to see if we have too many of those, all we have to do is take the determinant of our correlation matrix, and is that's not true, 0.000001, 4 zeros. And if the determination, if the determinant of our correlation matrix is greater than 0.00001, then we have no problem with high correlations. Now, guys, again, what's the big issue with high correlations? Well, it's that M word again, multicollinearity. That may be a test question. Spell multicollinearity. So, guys, let's jump out, go back to R. Let's run the determinant of our correlation matrix. And we get a value for the determinant of 0.074. So 0.074 is clearly bigger than this. And we have no issue, okay? Now, the next thing I told you that we would examine was what we call normality. And first of all, something I want you to know is normality is not an issue unless you seek to generalize. So if we're just worried about algebra and calculus and just looking at the underlying structure of displacement test, and we're not seeking to generalize to the larger population, then normality is not really an issue. Guys, normality, the easiest way is just eyeball, create some histograms and see if they look like they reasonably came from a normal distribution. If you're doing this as a master's thesis or with the intent to publish, you'd probably want to run a Shapiro-Wilk test. But I'm going to just show you one of these. So if I want to look at a histogram, for example, of calculus, then there's a little bit of right tail skewness there, but there's nothing that makes me leery that these scores didn't come from a normal distribution. Look at one more. And statistics, same thing. So the normality issue, I could go through and create histograms for each of the 6 variables. I'm not going to do that because it's something that you guys can clearly do. But, I don't see an issue right now with anything related to normality. Okay? Now, one thing about normality, big old red flag. I'm writing over here and you guys can't even see it, okay? So a big red flag, anytime you have dichotomously coded or Likert data, then clearly the normality assumption is violated for these 2 types of data. So, that's something that that you'd really need to address if you're using factor analysis or principal component analysis, if you have that type of data. Guys, I don't know. I think we're ready to get into some cool stuff. One more thing, sample size issue. I think we want 300. I think we need 500. And we'd love to have 1,000. Okay? We have 73. So you do the math. So is there a sample size issue? Yes. But the good news there is once we get into this reduction process, there's a determinate measurement that we can look at that actually tells us whether or not that sample size seems to be problematic with our structure. So, by the way, there's something called a Kaiser-Meyer-Olkin measurement. It's a KMO measure. If you were going to, I'm going to write this down just because, again, the purpose of all this is to put this stuff on your radar. It's not to really make you, excellent at ANCOVA or repeated measures or even factor analysis. It's just to put all this stuff on your radar to let you know that it is available when it comes time to potentially use it for research or your master's thesis. Okay? Wow, gang. I think we're ready to do some cool stuff. All right? Now, one thing I want you to kind of forget from the last video is there is a command in R called principal, and I think I used the PRINCOMP command previously. I like this one better. This is the one I'm going to use in this video because I like the flexibility that it gives us in transitioning from principal component analysis into factor analysis. And I'm going to do my best to make that very, very, very clear in this video. So guys, I tell you what, I'm going to get out of this. Probably not going to be over here much more. Everything we're going to do from here on out is going to we're going to look at in R. One thing to keep in mind: this principal command requires psych to be downloaded, the package psych to be installed. So. But if you're following along, you should have already done that. So, guys, what I want to do is I want to run my initial principal component analysis using my data set. And I want my number of factors to always be the number of variables. So again, I had algebra, trig, so on and so forth. I had 6 of those. So I want my number, and that should be factors, not factor. And I want my rotation initially to be equal to none. Okay? Now, before, with PCA, you have to run a summary, okay? Not for this one. If you run the summary, you're really not going to get anything that's that interesting. For the principal command in R, you just run what you've named the model, okay? Now, when you when you run this, you get a lot of stuff, okay? And I guess it's my job to go through this and to talk it through with you. First of all, notice that it's just calling the command. Notice that it's giving you a pattern matrix. Now this is, well, we've done no rotation yet, but there's something called an adjusted matrix and a pattern matrix. Depending on the type of rotation that we end up doing, it'll depend on the type of matrix that we'll actually look at, okay? And of course this is based on the correlation matrix. These scores right here are called the principal component loadings. And because we haven't done a rotation yet, these principal component loadings aren't of interest to us yet, okay? So let's just completely ignore those for now. Those 6 numbers with problem solving, we don't care about those just yet. Now, these H2s and U2s do mean a little something to us, but again, not just yet, but they will. Guys, this H2 column stands for the commonalities. Let me go back over here and write this down. So H2 stand for the commonalities. And U2, sounds like a band, right? U2, is 1 minus H2. And this is called the unique variance of each variable. So, flashing neon lights around this baby right here, okay? The unique variance. Now, guys, the one that we typically look at the most is the H2. And it's pretty, not that exciting in this data set because all of our H2s are equal to 1, but we've retained all of our components. We have all 6 components without rotation. So you can think about this kind of as your saturated model. Remember running that through, it's not a saturated model, but you can kind of think about it. We've retained all the components. We're explaining all the variation in calculus, trig, so on and so forth through these components because we have everything included. So guys, in the initial run, what I've got highlighted right here is pretty much irrelevant. But what is extremely relevant at this stage are the numbers that we get right here. Okay? Now, what I want you to know, well, I want you to know a lot of stuff. First of all, these numbers right here, 3.1, 1.35, 0.55, 0.49, 0.28, 0.23, those are called eigenvalues. And these eigenvalues tell us the percentage of variance that each of these subject areas explain. So for, I'm sorry, not subject areas, are components. So component number 1, the eigenvalue is 3.1. So 3.1 out of 6 components, which is 52%, which you'll see right there under the proportion of variance, is explained by component number 1. Component number 2 is 1.35. So 1.35 divided by 6 tells us that approximately, that about 22% of the variance is explained by component 2. 9% is explained by component 3, 8% component 4, and so on and so forth. Now, there's a lot of rules of thumb out there, but our focus is now turning on which components do we keep and which do we eliminate. And probably the strongest rule of thumb, the most consistently implemented rule of thumb that I see, is we keep all components that have eigenvalues greater than 1. So when I look at the eigenvalues here, 3.1 and 1.35, we get into principal component number 3, which is less than 1. It looks like to me right now that we have a 2-factor model. We need to retain 2 components because cumulatively these 2 components explain 74% in the variance, 74% of the variance that collectively trig, algebra, all 6 subject areas explain. So guys, it looks like to me that we're looking at a 2-factor model, but I don't know that yet. So let's just continue to explore some stuff and see what happens. Next thing I'd want to look at in helping me determine how many components I want to retain. And again, guys, as I said before, this is a reduction process. We're trying to reduce this thing down to the smallest number of components that we're still happy with the variance that it's explaining from the original observed variables. Now, another thing we can look at is we can examine a scree plot. And we get that by just plot. So I want to run my PCA, but I want to look at my, my values. from my PCA. And I want to run my type, first of all, as B. Now, these scree plots have the option of running the values by lines, points, or lines and points. So if you're running lines and points, which I'm going to do right here, you put a B for both, okay? Now, this is a scree plot, and this is another a picture that we can use to determine the number of components we need to retain. And what we need to look at here is what's something called a point of reflection. And a point of reflection is where our vertical tendencies and horizontal tendencies meet. All right, so I'm going to start right here at this point up here. And you can see that, again, look at these are nothing more than our eigenvalues. 3.1, 1.35, and so on and so forth. Now, if I start at my highest point and I come down to the first factor, notice my vertical move. When I come to my second factor, notice that I don't change much the vertical movement. But when I go from the second factor to the third factor, I start more of a horizontal move. So my vertical looks like that it's best from this factor to this factor. Now I'm going to examine the horizontal move. So I'm horizontal, not much change, not much change, a lot of change. So my horizontal move is from here to here. So if I look at where my horizontal move with my vertical move actually intersect, that's called the inflection point. Looks like to me the inflection point right here at the third component. So it looks like to me that we have a 1-2 component model that we need to retain. So I'm kind of focusing on two factors, all right? Or I should say two components. So I'm going to rerun my model. So I'm now going to call this PCA 1. So all I did with PCA, my original model, is just look at all of my components, all 6 of my components, same number of components I have, observed variables, and I'm looking to see, again, it's a reduction process. I'm looking to see which ones I can eliminate to reduce the structure of the model. So, guys, here I'm going to go data, but now I'm going to go in factors equal to, because from my previous analysis, that seems reasonable. And I don't want to do anything fancy yet. I still don't want to do any rotation. That's when things get really cool. All right, PCA 1, and I get something similar to what I got before, but I get something cleaner. First of all, I've still got a pattern matrix based on correlation matrix. That's just as before. But notice now that my principal component loadings have changed a little bit. This 0.82, negative 0.39, still not interesting. Why? Because we've done no rotation. Still not interesting, still not interesting, still not interesting. Am I making my point? Am I getting on your nerves yet? I'm getting on my nerves, not interesting. But what is interesting now are the commonalities and the uniqueness of the variance explained in calculus, trig, and problem solving. Now let me explain to you what this means. This 83 right here, this 0.83, is again the commonality. Now think about it, commonality, common variance, shared variance. 83 tells us that, the 0.83 corresponding to calculus tells us that 83% of the variance in calculus is shared variance. The spread in calculus is shared with other subject matters. Only 17% of the variance in calculus is unique. And that kind of makes sense because if you go into calculus, think about integrating. Sometimes being able to integrate requires, or I should say relies on algebraic manipulation. It relies on just arithmetic skills. Sometimes the ability or lack thereof to perform integration sometimes relies on your ability to add or subtract fractions. The least shared variance is in logic. So again, not interesting, not interesting. Okay, I'll stop. Interesting, interesting, and so on. But guys, there's nothing more interesting than this part right here. Well, other than this part down here. But for right now, let's talk about this. And if you look at it, nothing different, right? The only difference is instead of a 6-component model, we have reduced this thing to a 2-component model because these 2 components explain a cumulative percentage of variance that I'm happy with. 2. I don't think I gained anything by going to adding the 3rd component. Anything significant, okay? So guys, I'm feeling more and more comfortable with this 2-factor. Now again, let me say one more thing. Back here, notice before this was a 1, so 100% of the variance was shared. But guys, again, you had a full component model. You had all 6 components. You're going to lose some of that shared variance just because you've eliminated some of the components. All right? Now, is sample size an issue? Well, I was going to go back over here. Back to sample size. Now, the 300 that I talked about, 500, 1,000, was based on all the components. But now we're focusing on the 2 components, not 6 components, not the full model, if you will. So there's a rule of thumb that says that if the averages of our H2s are greater than 0.6, then sample size is okay for the current structure. And our structure is 2 components. So gang, I can go back over. Well, maybe, maybe not. I can go back over and look at the averages of my H2s. Guys, all of them are above 0.6. I'm feeling pretty good. Okay, so everything I have so far based on what's the correct number of components to reduce our full model to, I'm thinking the 2 is the correct answer. But guess what? Still not convinced. Always helps if you guys, if I put that where you can read it. Okay. So there's one other method that I think will help me out a lot. And what this does is it compares what's called our original correlation matrix with the reproduced correlation matrix. Now you can think of this as our components are equal to 6. You can think of this as our components equal to 2. So are these things are they comparable? And at the end of the day, you can just create a residual of these and take your original minus your reproduced, and you can actually get the difference in the correlation between what you started with and what you ended up with your last model. So let's go do that. Now, to get my reproduced correlation matrix, what I do is I go, I'll tell you what I'm going to do. I'm going to, okay, what do I want to do? I'm going to call this COR, okay? And I want to call this the reproduced. Okay, so the way I do this is factor model, and I want this off of PCA 1, and I want this to be off the loadings. So now if I take COR minus REP, I get the differences in the two correlation matrices. Now, a more straightforward approach. You can just create this right off the bat to get the same matrix. You can just do factor residuals, and we want our correlation matrix with our PCA, what, 1? Yeah. And you'll notice that you get exactly the same thing. So this is just the residual, the difference between the observed and what we currently have. And this is just doing the brunt work to show you that they're just a difference between two matrices. Guys, these differences should be small. So a good model, correct number of components. The differences in the correlation should be small. I think that's for obvious reasons. But another way for doing this is not only to examine the differences and just go through each and every item in the difference of the correlation matrix and the reproduced correlation matrix. Another way is to examine the fit based upon off diagonals. Remember way back, right here, this value right here that I told you would play a role. It turns out as long as that is greater than 0.90, then we have made a good choice in terms of the number of components. So as long as that's above 0.90, ideally we like it above 0.95, but the threshold also was 0.90. So guys, I am very happy with 2 components. Everything I see, the scree plot, the factor loadings, the drop off in the percentage of variance that's explained by the 3rd component, 4th component, 5th component, the 6th component. Again, the inflection point on the scree plot, this value right here being above 0.9, these values being very small in the difference of the correlation matrix and the reproduce matrix, I am a happy camper. I think that 2 factors is a perfect choice. Aren't you happy? Okay. So guys, let's review a little bit just for the sake of moving on. I told you this is going to be a long video. I'll probably have to divide it into 2 parts to get it uploaded, because we're getting ready to get to some cool stuff from here on out. So, first question. How many components should we retain? I would always retain the eigenvalues, the components that have eigenvalues greater than 1, and examine a scree plot. Now, where things get wacky is when these 2 things don't agree. And if that ever happens, that's when you just get into the literature and start seeing what you're supposed to do, which one you're supposed to agree on. One rule of thumb, I will tell you, is when the number of variables is less than 30, depend on the eigenvalues greater than 1 criterion. Okay? And the next thing, examine the model fit that we get from our output is greater than 0.90, ideally above 0.95. All right, boys and girls, I am ready to make some good stuff happen now. All right, so we're, or at least I am content with 2 factors, so let's start the process of rotation. Now, what I want to do is there's 2 types of rotation. There's orthogonal and there's oblique. And I am going to illustrate both of these for you. And this might be a good place where I actually split the videos, because I think this one's going to run into quite a bit. I can already tell my battery's about running down, so I may have to get that taken care of. So, but anyway, I want to do some rotation. So first thing I have to do is I have to install a package called GPA rotation. Oh, install packages. All right, so done. Let's access the library. Okay, now I'm going to run my second model, so I'm going to call this PCA2. And I'm going to use principal just like before, still data, ecstatic with my 2 factors. Because now we're going to bring in the most commonly implemented orthogonal rotation process called Variance. All right. Hit enter, type PCA2, and let's see what we actually get here. It looks like to me that the commonalities did not change, but clearly the eigenvalues did change. So now our factor loadings are much more interesting. So if I look down on component number 1, what I want to look at here is I want to look at the components or the eigenvalues greater than 3. Greater than 0.3. So guys, don't lose me now, okay? This is one of those drum roll please. You know, this is an important point here. we're trying to find out this underlying structure. We're trying to find out which variables load on component 1 and which load on component 2. Actually, since we've done the Varimax rotation, we're actually going to call these, begin to think of these as factors instead of components. So it looks like to me that calculus, trig, and algebra are all greater than 0.3. So it looks like to me that calculus, trig, and algebra are loading on component 1. And it looks like to me that problem solving, logic, and statistics are all loading on component 2. Now, something that might help there is such a emphasis put on this eigenvalue being greater than 0.3, dictating what loads on what component. So there is a print psych option, and we can run it for PCA 2, where the cut is equal to 0.3, and I want to sort equal to be true, and this is just going to put it from high to low. So what happens then is it gives me just a better visual on what's actually loading. So you can see that the factors that load highest on component 1 are trig, calculus, and algebra, and the ones that load on factor 2 are problem solving, logic, and statistics, and it sorts it from highest to lowest. So our commonalities and our uniqueness still haven't changed. Okay. And notice that we're still right at 3/4 or 75% of the variance is still explained. Okay. Well, guys, I'm a happy man. If I were really publishing this, I would be extremely happy. And let me show you why, because it's all starting to kind of make sense. And it's crazy how many times this does make sense, okay? So rotation has clarified our model. Somewhat, okay? So factor 1 loaded calculus, trig, and algebra, while factor 2 loaded stats, logic, and problem solving. These are all observed variables. But I think you can see the construction of some latent variables emerging from the commonalities within each factor. So the latent variables, at least for me, for factor number 1, it's amazing how this falls out, are things that require symbolic manipulation. The latent variable underlying factor 2, statistics, logic, and problem solving, I don't really know what I would call that. Maybe more of a liberal arts math. I don't know. Probably a better term for that. That's one of the most frustrating things about once you run factor analysis and you get these things that load on these particular factors. What do you call them? And sometimes that's really kind of crazy. Now, let me tell you something that may happen is let's say, for example, you, and this happened to me one time. I had question 1, question 2. I had 25 questions from a developmental math test. And these things emerged on factors. I remember they were three factors that emerged, and these went different ways, right? Well, all the questions that emerged on factor 1 were out of chapter 1, probably chapter 2, whatever it may be. All of these were out of chapter 2, and all of these were out of chapter 3. Not necessarily factor 3 was out of chapter 3, but factor 3, these questions all came from the same chapter, except for a couple of questions. So what I ended up doing to tighten up the model is the questions that didn't load naturally on the particular factor that corresponds to the particular chapter, is I came in and just deleted those, and it just really strengthened up the model. Okay, so that could be something that you'll run into. So, gang, let's get back to R and see what's happening here. So again, I'm feeling really, really, really good. Okay. Now, what do these numbers mean under RC1 right up here? These loadings. What this tells us, I'll tell you what. If this were a negative number, and sometimes these numbers are. It just tells us that a high score on the factor indicates a low score on the subject, because we're ultimately going to create what are called factor scores, and so again, higher scores on the factor indicate a lower score, but these are all positive. So this tells me that a higher score on this first factor indicates a higher score on the trig factor and calculus and algebra, and the same thing for factor number 2. Okay. Now, guys, doing a lot of jumping around here, but it's just one of those things. Orthogonal rotation. Which we used with Varimax, assumes that RC1 are uncorrelated. So it assumes that symbolic manipulation and liberal arts are independent. They're not correlated. Now, is this true? Probably not. And when you can justify that your components probably are correlated, then you get into a situation where you may consider a different type of rotation. Now, guys, orthogonal rotation just says that we turn things, think about it simplistically, 90 degrees. Oblique allows us to make more sophisticated types of rotations. So what we can do to run this is, well, I'll tell you what, let's just go run it. So what I want to do now is I want to create a new model. But I want to run an oblique rotation. So I called the last one what? PCA 2. So I'm going to call this PCA oblique 1. Still principal. That's what I like about that. It's gives us the option of doing orthogonal and oblique rotations. But the rotate I want to use here is OBLIMIN, I do believe. Yeah. So I got PCA OB1. And everything pretty much looks the same, right? There's only one thing that's additional. These things right here are still your factor loadings. Notice that our commonalities and unique variance didn't change. These things here are still called our eigenvalues. But the thing I like about running the oblique is it gives us the correlations between the two components. Now, if I had correlations between component 1 and component 2 that was less than 0.3, then I would feel comfortable with just reporting what I got from the orthogonal rotation. But you know, again, it's a close call, but with the 0.35, I would feel more comfortable controlling for that and running the oblique rotation, which we just did. Now, the tough part about oblique rotation is the following. Orthogonal rotation is, well, regardless of the rotation, we get into two types of matrix. We get into a pattern matrix and we get into a structure matrix. Now, for orthogonal, these two are the same. For oblique, these two aren't the same. So, guys, it should be pretty commonsensical from here that since we ran the oblique, we need to create the structure matrix. Okay. Now, again, by default, the principal creates what's called your pattern matrix. So we're going to come in and look at our structure matrix and see if there's any difference. This is quite a lot to type, and I have to write it down. So, see, what we call this? PCA OB1. So PCA OB1, and we want to look at our loadings. So it's just multiplying two matrices. Times phi. And phi is just the transition. We think of phi as being the angle between the rotations. All right, just checking my. So, guys, our structure matrix looks like this, and I want to compare those. It looks like to me, let's see, 0.89. So the structure matrix has, let's look at things bigger than, so 0.90, 0.90, 0.89. So there's consistency around the 0.9, telling us calculus, trig, and algebra load on component 1, and then structure consistency around the 0.8 mark, telling us stats, logic, and problem solving load on component 2. So, guys, I think that the structure matrix and pattern matrix support what we knew all along from the orthogonal rotation. So guys, again, I'm a happy man. If I were publishing this, I would be extremely, extremely happy. Now, we'll focus on factor scores. And factor scores are extremely helpful for us just in case we want to use these latent variables in future analysis. So guys, I'm going to do final PCA. And so I went principal. So this is going to be the drum roll, please. Data. So we know through all of our hard work that we went 2 factors. We know from the correlation matrix between component 1 and component 2 that we have reason to believe that we need a oblique rotation. But now we want to include our factor scores. And you type final PCA and you're like, wait a minute, what Darbo do to us? There's nothing different. Well, just because you created the scores doesn't mean you yet see So I'll have to go final PCA, $ scores. And we get our component scores for each of the students. Okay. Now, essentially, these scores just tell us how these how they score on each component, really, and so it compares subject 1 on symbolic manipulation to subject 1, same subject on liberal arts. Now, the beauty of factor scores is you can use these in future analysis. So let me give you something that a couple of scenarios. Let's say, for example, that we had all these scores, and we wanted to, but we also had some ACT scores. So, guys, I'm just going to create some ACT scores here randomly. So to go along with this, so I'm going to go R norm, and I'm going to create 73 of them. From a mean of 21, standard deviation 5. And I want this to be rounded to 0. So guys, when I get my ACT scores, you can see I've got 73 ACT scores that I just created randomly. So don't put a lot of stock in this because those were just created randomly. Okay? Now, what I could do is I could create new data 1 and create, I'll tell you what, let me get the names of data. Okay, so I could create new data number 1 where I'd create a data frame with calculus, trig, problem solving, logic, stats, algebra, and ACT. And you can see I have a new data set. Okay? What I could now do, if I wanted to, is I could try to predict ACT using a linear model. So ACT predicted from, no, we'll get these. Okay, so I want to predict ACT. I'm sorry. So I want to predict ACT from calculus plus trig plus problem solving plus logic plus stats plus algebra and I get no statistical significance. Got standard errors that are relatively high. Guys, I got major multicollinearity going on, because if I go back up to my original matrix from many moons ago, I see that I have some variables that are highly correlated. Let's see, what do I actually get into that was highly correlated? Looks like trig and calculus are pretty highly correlated. Really, after I look at this, it's not as much multicollinearity problems as I thought. We could run some variance inflation factors and tell for sure. Another way to do this is to get, let's see, what did we call the scores? TC1 and TC2. Okay, I got to some way go in here and save these scores. Final PCA scores. Okay, let me. All right, let's save these as. All right, so let's go new data. I'm not even sure this is going to work. Yeah, okay. Now, what I could do is I could run a model. As I'm losing it here, this has been on new data too. And you can see that it's saved TC1, which would be symbolic manipulation. And TC2 would be liberal arts, and I can predict ACT from that. Okay, what am I going on here? Okay. All right, this should do it. If not, I'll have to get back with you on this one. Yeah. So I go summary, model 2, and you can see that, well, neither one of them turned out to be statistically significant, but you think about it, I randomly created those ACT scores, so you wouldn't think that there would be much relationship. So guys, in times of that we're wanting to identify latent variables, these underlying constructs, such as symbolic manipulation or liberal arts skills, or depression, or bullying, or whatever it may be, these things that aren't necessarily observable in terms of data that we can collect, then this process is very helpful. It's also going to be extremely helpful when we get into test theory. Well, guys, that is it. I am tired. I'm ready for this to be over. So that's it. Take care.